take a look at the system of linear equations. L1 x plus m1 y is equal to P, and L2 x plus m2 y is equal to Q. This system of equations can have a unique solution, no solution, or infinitely many solutions. Let's discuss the case when the system has a unique solution. The given system of linear equations will have a unique solution if L1 upon L2 is not equal to M1 upon M2. That is, if L1 into M2 minus L2 into M1 is not equal to 0, then the system will have a unique solution. You have learnt that a given system of linear equations can be expressed in the form of a matrix. So, on representing the given system in the form of a matrix, we obtain the equation shown. Let us now see how we can define a unique solution of a linear system in terms of a matrix. Consider the 2 by 2 matrix with the elements L1 and M1 in the first row, and L2 and M2 in the second row. The real number L1 into M2 minus L2 into M1, which is associated with the matrix, can be obtained by multiplying the diagonal elements and then subtracting the products. This real number is known as the determinant of the 2 by 2 matrix. Let us now define determinants in terms of functions. Let A be a set of square matrices and B be a set of real or complex numbers. Also, let f be a function from A to B, defined by f of x is equal to b, such that x belongs to A and b belongs to b. Then f of x is called the determinant of x. Determinant of A is denoted as det of A or delta. A determinant can also be defined as a function whose domain is a set of all square matrices and codomain is the set of the union of real and complex numbers. If A is any square matrix, then determinant of A is denoted as shown. Note that determinant of A is not modulus of A, as a modulus exists only for real numbers. Also note that determinants exist only for square matrices. Moving forward, let us learn to evaluate the determinant of a matrix with real entries up to order 3, beginning with the determinant of a matrix of order 1. Consider a 1 by 1 matrix A. The determinant of matrix A is A11. Observe that the determinant of a matrix of order 1 is the entry in the matrix itself. Next, we have the determinant of a matrix of order 2. This we have already discussed. In this case, det A is equal to A11 into A22 minus A12 into A21. Lastly, we have determinant of a matrix of order 3. Consider the general form of a 3 by 3 matrix. The determinant of a third order matrix can be determined by expanding it along a row or a column in terms of a second order determinant. This is known as the expansion of a determinant. The determinant of matrix A can be calculated in 6 ways as shown. Let's discuss each case one by one. First, let us learn to expand the determinant along the first row. Beginning with the first step, multiply the first element, A11 of the first row, by minus 1 raised to the power of 1 plus 1, where 1 plus 1 is the sum of the suffixes of A11. And then, by the second-order determinant, obtained by deleting the elements of the first row and the first column of matrix A. This is because A11 lies in the first row and the first column. Hence, the product corresponding to the above step is as shown. In step 2, we multiply the second element A12 of the first row by minus 1 raised to the power of 1 plus 2, where 1 plus 2 is the sum of the suffixes of A12. And then, by the second-order determinant obtained by deleting the elements of the first row and the second column of matrix A. This is because A12 is an entry in the first row and the second column. The product is as shown. In step 3, we multiply the third element A13 of the first row by minus 1 raised to the power of 1 plus 3, where 1 plus 3 is the sum of the suffixes of A13. And then, by the second-order determinant obtained by deleting the elements of the first row and the third column of matrix A. This is because A13 lies in the first row and the third column. The product is as shown. Lastly, we add the results of the 3 steps to get the determinant of A. The determinant of A is as shown. On simplification, we get the required determinant of matrix A. Let us now apply these steps to expand the determinant of A' along the first row. The first entry of the first row is 2. Multiplying it with minus 1 raised to the power of 1 plus 1, where 1 plus 1 is the sum of the suffixes of A11, which is the position of this entry in the matrix, and then by the second-order determinant obtained by deleting the elements of the first row and the first column of the determinant. Similarly, the other 2 terms can be obtained. On simplifying, we get determinant of A' is equal to minus 37. Similarly, the determinant can be expanded along the second row by the same method. This is the required determinant of A. Let us now find determinant of A' again by expanding it along the second row to understand the concept better. The first entry in the second row is 1. Multiplying it with minus 1 raised to the power of 2 plus 1, where 2 plus 1 is the sum of the suffixes of A21, which is the position of this entry in the matrix, and then by the second-order determinant obtained by deleting the elements of the second row and the first column of the determinant. Similarly, the other 2 terms can be obtained. On simplifying, we get determinant of A dash is equal to minus 37. Observe that the determinant of A dash, when calculated along the first row or the second row, is the same. In general, we can say that calculating the determinant of A dash in any one of the 6 ways yields the same result. Let us now see the remaining 4 ways in which a determinant can be expanded. Following the same 4 steps, determinant of A can be found on expanding it along the third row, as shown. The required determinant of A is as shown. In a similar manner, the determinant of matrix A can be expanded along each column. Observe that the value of the determinant of matrix A yields the same result when evaluated along rows R1, R2, and R3, and along column C1. Similarly, the determinant of A will be the same along columns C2 and C3. In this way, the determinant of a square matrix can be found along the rows or along the columns. Some important points to be kept in mind while finding the determinant of a square matrix are: if any row or column contains maximum number of zeros, then finding the determinant along that row or column makes the calculation easier. If all the elements of a row or a column are zeros, then the determinant of that matrix is 0. If M and N are 2 square matrices such that M is equal to K into N, where K is a real number, then the determinant of M is equal to K raised to the power of N into determinant of N, where N is the order of matrices M and N. At the time of expansion, the ijth term can be multiplied by +1 or -1, depending upon whether I plus j is even or odd, instead of multiplying it by -1 raised to the power of I plus j.